I'll figure it out later. Okay, I can start out without using auto. So today I'm going to start talking about some kind of well, two different topics. I'm going to talk about debouncing, and then I'm going to talk about like carry look ahead adders, which are both really actually quite interesting. So let's start with debouncing. Debouncing is a solution to a problem that you guys probably don't realize exists. So if you pull out your basis board and you were to look at it, it has those switches and the push buttons, right, that we're using as inputs. Right now, we don't really care because we're just throwing the switches to turn on lights, more or less, right? Not going fast. But let's say that you wanted to design a digital system that counted the number of times that you pushed the button. Well, it turns out that when you push a mechanical button, it doesn't go whap and stop. It goes blah, 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 blah. Yes. So each time you push it, it's going to count a bunch of times potentially, and that causes problems, right? So how do we solve it? There are actually a couple of different ways. The dumb way of solving it is to just put an RC filter at the output of your switch, right? That's helpful. It'll solve it, because then if it goes flap, 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 when it first hits, it'll start charging, and then it'll start discharging, and then start charging and discharging, but it won't actually cross over that detection threshold from 0 to 1 until the RC filter has had time to get there, right? The problem is that if you look at CMOS technology, your capacitors are big compared to all other devices, well, except for inductors. Inductors are huge. But capacitors are big devices compared to like transistors. So we can actually use dozens of transistors before we're the same size as a typical capacitor that you might want for this kind of filtering. So that's a problem. The basis board may, right, because it's big, it's bulky, it doesn't really matter. They may put RC filters on the backside. I actually don't know. I don't think they did though, because I think they left it for learning so that they could purposely be bad, right? So the next one that you can do, which is an upgrade, is go ahead and bring back our old friend, the SR latch. And then all you have to do is into the set and reset, you have two different ports. One of these ties up to there, and then this one will tie up to there as well. It's all the same line. And now you have this system. So this is my button, right? Instead of having just a contact or no contact, now I have to have what's called a single pole double throw. So let's introduce some switch terminology. Single pole, single throw. This is what your push buttons are. It is either disconnected or connected, right? That's all it does. Whereas single pole double throw is this. There is one input, single pole double throw, two locations that it can go to. Okay, so it is either connected to reset, so either reset or set is ground. But there is a pull-up resistor that is making sure that it behaves a little bit better. So what happens is, let's say my default position is reset. So I'm defaulting to 0, right? And if I push this button, it's going to throw it to the set position. Now, what's nice about this is we're pulling up weakly. We're using like 10K resistors here, something pretty big. And the other nice thing is these can actually, because they can be big, can be transistors, right? Because you can use a transistor as a resistor. So it can still be small, because small means big resistance. And since we're talking about human inputs still at this point, they can be very big because the time scales don't really matter, right? Because humans are super slow compared to a 400 megahertz clock. So any capacitance at this input plus a big resistance is going to make a nice slow kind of characteristic. Moreover, we're grounded, it's going to throw up and go say set. And we know that if we set an SR latch right, it goes to 1. And what's nice now is, so these are active low, right? They have to be, that's why this ground is, I guess I should make that clear, they're active low. So what's happening then is I push set, I want to go from 0 to 1, it goes and hits set. It does set, right? Because an SR latch is combinational logic. It's not looking at any clock, it's not doing anything, everything's fine. So it goes and hits, it sets, it bounces off of that. But it doesn't bounce all the way back to reset. So what happens is it goes set, 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 which is fine, right? Because that's just saying B1, 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 1, 1, 1, 1. Right? It's just telling it to be that 1 over and over again. That's not really a problem. Make sense? So this is a nice way, but this single pull double throw can be an issue because lots of push buttons, for example, are not that. They are single pull, single throw. So I need, if I want to have something that can accommodate this type of switch, this type of input, I need to take it a step further, which turns out to be not that big of a deal either. So if I have my input and it bounces like this, and then I'm going to throw it and it's going to bounce here and up there, right? So this is my input. I want to take that input, let's throw it into a flip-flop. There's going to be a clock on this flip-flop. It's going to come in here. The input goes into the D port. Right now, I'm going to only be concerned about Q. And let's think about what happens now. So if my clock is ticking along, let's throw here. My clock ticks along, right? So what happens to Q? Well, let's say, because there's no bubble on the clock input, right? This means it's a rising edge triggered flip-flop. So let's assume that it starts at 0. Because there's no clock here, I have to either say we don't know or start with an assumption. So let's say it starts at 0. Well, the first time it updates is going to be this rising edge. It's still going to be 0. I haven't thrown my switch yet, it's still 0. Nothing happens until the next rising edge, right? We're familiar with timing diagrams, we remember this stuff. Here, let's assume a small delay, just for the convenience of drawing it. And it's going to update for 1, and it's still 1, right? Because it's 1, 1, and it's not until here, with a little bit of delay, that we drop back to 0. Okay, well, because we're using a flip-flop and we're synchronizing the updates to this edge, we are avoiding this bounce. Does anyone see why this is not quite good enough? Exactly. What happens if it hits in the middle of a bounce? Or more accurately, as well, not more accurately, in addition, what happens if it hits near any one of these edges? Even if it's the end of the bounce, it catches the edge, right? We violated setup and hold. Well, up until this point, I've explained that, well, what really happens is we don't know what it is. It's actually worse than that. If you clock in near the edge of a transition, you can end up in an oscillation. So it actually just triggers back and forth 0, 1, 0, 1, 0, 1. Now, the probability of that is super small. Like, you have to be within less than a propagation delay of the rising edge. So the probability of this happening is very small, but it is a real possibility. So you throw it here, you don't really know what it is. That's okay technically, because then you're still going to be delayed 1 clock cycle and you'll update, right? So is an issue to update in the middle. Worst issue is that you might oscillate. Both of those can happen. Fortunately for us, there is a really nice and easy solution. Oh, one thing that I need to say then is for this one to work at all, you need your clock period to be long compared to the amount of time that you have a bounce. So we have to create a fairly long clock divider, like a fairly large clock divider, and able to make a small clock to make this happen. Because 400 megahertz is still very fast in mechanical bounce terms. So if I were to try and do this with a 400 megahertz clock, there's no way it looks like this. There's gonna be like 100 and something clocks in this region potentially. So you're gonna be all over the place. So, I mean, depending on your circuit, right? Different switches have different bounce characteristics. The littler they are, the better they tend to be. But anyways, I'm not a mechanical engineer. I don't know all the details of it, but it can be an issue. So you want to make a slow clock. Making a slow clock takes a lot of circuitry, right? Because it's a clock divider. Divide it down, divide it down, divide it down, divide it down. Every time you divide it down, you have to add more logic. Okay, well, we're gonna have to be stuck with that for a while, but let's go ahead and address the other issue, right? Which turns out to be really easy. So we just throw a second flip-flop. D, let's just take the same clock. Q. Okay, so now what does this change? Well, if I have the rising edge of a clock here, yeah, labeled a Q, so let's go ahead and call it Q. And it's, say it starts at 0, rising edge of a clock, it's looking at D, but it's triggering at these same points. Well, there's this little bit of delay, so this rising edge is still 0. So it is delayed till here before it transitions, and this guy before it transitions back to 0. Okay, this is why I like to do these little delays, right? Just so that we remember that there is delay, so it's going to update. In general, this is helpful because your clock to Q delay is generally going to be longer than your setup and hold times, and it's just the nature of the propagation delays inside the flip-flop.
Keep stacking them until you get
Not quite. So this one is actually sufficient that even if this one goes into oscillations, those oscillations are highly unlikely to fall again on the rising edge of the clock, right? So basically what we've done is taken a very low probability and multiplied it by a very low probability, and now we have an absurdly low probability of having any issues. Generally, the rule of thumb is you don't need any more than 2. If you wanted to do a third one, sure, why not? Right, it's just going to multiply the probability, reduce it. But generally, this is sufficient for some very basic debouncing. But there is one more concern, one more issue that we have left to deal with. In this case, we still need the slow clock. Not really that big of an issue in an FPGA, right? We have tons and tons of logic. But the next one that we want to do is we want it truly synchronized to the system, which it is. It's doing a decent job of synchronizing here. But I've talked about, especially in high-speed systems, like your ready signal, right? Where you want it asserted for 1 clock cycle. You just want it to flick on and flick off. That's pretty standard design criteria for a lot of systems that you're going to get. Is ready is going to last for 1 clock cycle. Now, what I've had you do in the past is use your state machine, right? You can use the state machine transition to update your ready signal. So for example, I'm sitting in the state, let me do just a couple of clock cycles here to illustrate the issue. So I want to assert the ready signal for my UART, okay? Well, let's say before this clock, I'm sitting in the, what do we call it, stop bit state. And stop bit is going to assert actually, let's say this is data bit, and so this rising edge is where I enter stop bit, okay? That's going to assert ready. This rising edge is where I'm going to enter idle, okay? Idle. So idle sets it back to 0. So notice, shoot, did I do this wrong? So you need the clock that you go into, it takes one more clock than that. That's why I'm doing it. So we update and say, okay, on one of these clock cycles, we want to assert this. And at the same time, we're going to say, hey, our next state needs to be idle, and we'll eventually transition, and your rising edge ends up lasting for 2 full periods. If you go and look at your timing diagram, there is a way that you can do it in one. This way is going to simplify it. In fact, everyone I've looked at will do this, more or less. It is, did you say yours is 1? Okay, yeah, so it is possible to do that. Most people end up with 2. There is an easy way, even outside of state machines, to make sure that you don't have 2 clock cycles of ready. And it is using this logic. Now, it's going to offset it by 1, but all we have to do is say, well, let's take this guy and throw this into an AND gate. And then from here, let's just take not Q. So not Q is the same as this, but in reverse. Okay. And now, what does that AND gate see? Well, it sees it's going to output true if this signal, which I've ended up calling Q, that's Q. That's D, unfortunately, isn't it? My bad, bad labeling. We'll stick with it for now, though. Okay, so it's going to take D and not Q. Well, where is that true? Only right here. So the output ends up just going 0, 0, 0. This one rises. Not Q is still 1. So it pops up. Not Q drops to 0 a clock cycle late, right? The second flip-flop. So it drops back to 0 and on to 0. So this only detects an edge, right? This is a rising edge detector. Click, sends a pulse, drops, it's done. So you can use the debouncing circuit, which is helpful for problems, to also build a rising edge detector. Make sense, everyone? Great. For debouncing, we still need it to be long clock period. There's no real way around that, but well, there is, right? RC circuits can do that. But anyways, that's debouncing. Any questions on debouncing? Cool. I'm going to erase everything, and we're going to completely switch gears to something that I think is really cool. Okay. So I've talked in 2700 and in 3610 ad nauseum about adders, right? You take full adders, you string them together, you end up with an n-bit adder, right? Talked about how we can use generate and generics to automate building, say, a 32-bit adder. But what's the problem with a 32-bit, what we call ripple carry adder, right? So a ripple carry adder is where I take a series of full adders and I just start stringing them together, right? What's the problem with this type of adder? The delay is each bit that I add adds a propagation delay of at least 3 gates, right? If you think about your logic, it ends up the optimal result, the optimum size of a full adder takes 3 gates. You can build it with 2 gate delays, right? Because if you just use the direct solution method of K-map, you will always end up with 2 tiers, right? The ands and ors and ands, sum of products, product of sums. 2 gate delays is your minimum. Realistically, most of them end up with 3 gate delays because of it takes fewer gates to do it that way, right? Which I won't get into yet. So every bit I add adds an additional delay. If I want to add 32 bits, like a lot of operating systems kind of do, that takes a very long time. So we want to come up with something clever that doesn't take a very long time, okay? So there is always going to be some trade-off in digital logic, and a very common one, you can trade speed for complexity. So if you want to go faster, you have to make a more complex circuit, right? So I'm going to walk through something called a carry look ahead adder. The reality is you won't need to build one of these ever in your life because you can just make it using, like if you write an addition, it will decide whether it needs to be a ripple adder or a carry look ahead adder when it synthesizes. It knows for you. However, why I think this is cool and useful is it introduces you to some of the more advanced design concepts that will help you develop future algorithms. So if you end up trying to build DSP components, understanding the CLA, carry look ahead adder, is like the first step, because this is one of the easiest to grasp complex systems. Next time, I believe, we'll talk about multipliers, and those start getting really cool. And my target isn't so that you know how to build these. I mean, I want you to understand them so you know what's going on behind the scenes and you're aware of potential pitfalls if the synthesis goes weird. But the main thing is to help you guys develop your digital design skills, okay? Is thinking about how we can treat digital design different than other types of design processes. So what the carry look ahead adder does is it realizes the assumption that we know, given 2 numbers, that if I'm adding these 2 together, I can already tell that this column is going to have a carry out. And this column is going to have a carry out, right? This I know pretty much instantly. And I can write that as simply saying, and I'm going to call this one for future reasons, generate. Is my bit at a given index going to generate? I'm going to, for you, this is A, this is B, I'm just labeling them. Is it going to generate me a new carry? So any given index is A at I and B at I. If both are true, I know I'm going to make a carry in that column, right? So with one AND gate, I can already start saying I'm going to make a carry. Well, what happens here? Well, this one is going to end up with a 0, 1, right? Remember addition, right? And then we have a 2 plus 1, which is going to end up with another 0, 1. So this guy generated a carry, kind of, right? Because he didn't make it. He did what's called propagating it. So what are the conditions for propagation? Well, we're going to create a propagation function, and I'm going to call that P at I. And what P at I does is it's just saying, well, I'm not going to tell you whether or not there is a carry yet. I just want to tell you if there could be a carry. And the condition for could there be a carry is AX or B. If I have either one of those, I could make a carry. Now, the reality is I could probably just say A or B, because if I have two ones, I am still going to make a carry, right? But that's already covered for it. I don't need that condition because I've already accounted for A and B. So let's throw that out of this expression. So then all I need to consider is that, well, if I can make a carry and there is a carry, meaning that I generated one, then I'm going to have a carry. Okay, so the other way of looking at it is that sum is going to be true if you have A, X, or B, right? Because if either one of those is true, this makes a 1. X or C, because we need to account if there is a carry and A and B are both 0, we need to make a 1, right? So that's all this is saying, is A, X or B, X or C. But we need to consider, where is this CI coming from first, right? We need to make this carry. So let's get there. Well, the first thing that we'll do is rewrite SI. So AI, X or BI, right, is, well, A, X, or B here. So we just have propagate and carry. Sorry, not and, X. So this propagate function, I'm just reducing to here so we can, yes?
Some also be true of A, B, and C.
We'll get there.
Oh, okay.
It's actually, it's kind of nice the way it ends up working out. But it's not obvious, this will cover it because of the carry. Okay. So now let's consider the first carry situation, right? Because that's always the easiest one. There's nothing else coming into it. It's easy to express. That first carry is just going to be, did it generate one, or can it propagate one and carry? Right? So if it's possible to propagate and there's a carry in, we're going to assert the carry. Sorry, this is I plus 1. So the next carry is dependent on the previous carry. Right? Fortunately, in the first one, there can't be a carry, so it's just, did I generate one? So the first one's expression is super easy. Well, what happens when we get to carry at 2? Well, it has to look back and say, did any of the previous ones make a carry that I have to care about? Right? So then when I want to get to carry, so carry 1 is easy because it's just, did I generate? Oh, sorry. This is carry 0 because it's 0 index. Carry 1 gets a little complicated because it has to go, well, did I make one? Or P0, C0. Can I and did I? Right? Well, whether C1 is asking, did I, or did the previous one have the ability to and did it? What was it saying? Well, C2. Unfortunately, C2 now has to look all the way back here because he created a carry this one generated it, it got propagated, right? Now this propagation carry. So it's looking at this P0 going, okay, we could have a problem. I guess I could write this as C1, G0. That now third column, which is carry 2, is saying, did I make one? Or did this happen? Let me just actually write this out. Or did P1 have the ability to propagate and the last one generated one, right? So this guy generated, P1 propagated it, right? This is saying P1 passed it along from 0. Well, or do we go all the way back and did this original carry pass to P0, pass to P1? So this term is only necessary if there can be a carry in, essentially, right? That's the question, is can I bring in a carry? Which we may want, right? Because we can build a system where I build a 4-bit adder and I just start stringing the 4-bit adders together. So I may want to design my 4-bit as being able to have a carry in. So I do that, I need to start looking at the possibility of this guy being CU0 because I can bring a carry in, right? So we may have to shift by 1, but if not, we can use this as our initial. Does everyone follow that? Didn't confuse you? It's okay. There's 2 conditions, right? Either I can have a carry in or I can't. Okay, well, unsurprisingly, C3 gets worse, right? Does it have a carry out if he made his own, or let me make sure I do this right real quick, but basically you can see where it's going. We generated something at 0 and we propagated it down the line, or we generated something at 1 and we propagated it down the line. So G2 propagated with P2. Or, sorry, I got lost. All right, P2 G1. Did 1 generate and P2 passed it along? That's that question. Now this one is, did the 0th bit generate 1 and pass it to P1 and pass it to P2? Okay, so we're looking at all the possible places we might make its carry, and did we pass it along? That's why we're calling it these propagate functions instead of making P, right? So P we could have written initially as AX or B and C. But we don't, because we want a propagate function that says, is it enabled? Did we allow the possibility of being propagated?
So we have an or C0, P0, P1, P2.
Yes. P2, P1. Right, so we only have to worry about passing it down the line. So the G1 only has to pass to P2. G0 has to pass to P1 and P2. C0 has to pass through P1, P0, P1, and P2. It's asking all. So you can see where this is going, right? If I write C4, so if I tried to build this into a 32-bit adder, I have a nightmare of AND gates building. But it's fast, because what's super awesome is that, well, a couple of different things could happen. Either I have access to 4 input AND gates, and this is my propagation delay is only 2 gates, right? Because it's the and then the or. The worst scenario is I only have access to 2 input AND gates, and these guys have to be cascaded a little bit, right? Remember how to make tiered AND gates if I only have 2 AND gates? Right, so to make a 4 input AND gate, I need 3 AND gates like so. But what's nice is my third carry, then, his worst case path, he's still going into some big AND OR gate essentially, right? And this OR gate is the same situation if I only have 2 input OR gates. And so my path is 1, 2, 3, 4. 4 gates for a 4-bit adder. I've cut it in half, which is nice. And actually it gets better and better the longer I go. And what's nice is on your FPGA, this does not implement in 2 input AND gates. It actually probably implements in a lookup table, like I've been having you guys puzzle through the last couple of homeworks, right? Because those are fast. It's just a mux, right? It just throws it in and outputs it. It has like 3 gate delays and you move on. So this can get very, very fast when you're doing it that way, but it gets very, very complicated. The size of your logic gets very large to do this. So that's your trade-off, right? That's what this kind of understanding is valuable for, is this kind of quickly illuminates why when I say there are trade-offs between speed and complexity, right? Makes sense because you can see it. Which one do I want to erase for this? Probably these guys, because I think they're okay. Okay, well, what if we don't need to go that fast? What if we want to start playing a balancing game? I need to go a certain amount of fast, but I don't need to go as fast as I can, right? Well, we can build these trade-offs really simply. So this is where we start being able to adapt with a sliding scale of speed versus complexity. It's not a one or the other, it is a sliding scale. So if I were to look at the initial one, they call these partial full adders, and they're going to have a G and a P, right? Generate, propagate outputs. And then it needs a sum and a carry, which is its input. Okay, and that's all. I don't actually need the carry out. And then up here, AI, EI. So those two plug in, it throws out the sum, the generate, and the propagate, but it needs to consider its carry in. Now there's a reason I put this carry in down on the bottom and put the input arrow, and that's because if I want to start stringing these guys together, this guy is what we'll call the CLA logic. Right, and the generate and propagates get thrown in the CLA logic. This is where you coded those big long equations that I just erased, right? P's and G's gets thrown into that, and it decides where to route the results. Well, this is what I just showed you, but there is kind of a better way where instead of calling this a partial full adder, let's go ahead and call it a 4-bit CLA. Well, now these P and G don't work quite the same, but guess what we can do? We can start generating group propagates and group generates. Does the group as a whole propagate, or does the group as a whole generate? And all you have to do for that is my propagate function is internally, let's look at P3, P2, P1, and P0. Does it pass all the way through? Right? That's the same as those previous equations, but we've rewritten the propagate function into one big one. Then I can write my generate as, did my last one make one? Right? That's the only one I care about, because otherwise it's a propagation function. Or generate. Did I make one? Did the second one generate and propagate? Generate, propagate, generate, propagate, right? The nice thing is, none of my equations inside of the CLAs get more complicated than that. So they create these group propagates and group generates, and then I just have to go in and use the same type of CLA logic, right? It actually doesn't really change to determine each of these groups of 4. Make sense? So now I've decided that I'm okay with 4 propagation delays in each of my adders, and then I'll combine them into carry look ahead. I can adjust how big these bits are in order to adjust the level of complexity that the generate statements are versus the speed, right? It's not an analog tuner, right? There's very discrete steps, but I get to choose 1, 2, 3, 4, 5, 6, 7, 8 bits, however I want, in order to tinker with the speed of my carry look ahead. Any questions on that? Okay. At this point, I kind of want your input. So a lot of these lectures are going to end a little bit early. This one case would be 30 minutes early. Will you guys find it more useful to watch me put together how you would do something like this? Or do you want to spend time on your lab? Any other strong opinions? So it was going to be next Wednesday. Instead, it's going to be the Monday after, so that you guys have the whole weekend to study. I've updated a course schedule, and I'll post that today so that you can have the updated version of that. So no strong opinions other than wants lab time. It's okay. So the book does have the code for this that walks through. The only caution that is, if I was going to do this walkthrough, I wasn't going to use it as anything other than a reference, because they use some weird architecture. Let's just put it that way. Because they use a thing that you can do that I don't really teach, where you can have, where we have an entity and then we list through it and then we end the entity. They have multiple architectures inside of one entity, which you are allowed to do, but I don't teach it because it confuses good design, because it makes you stop thinking quite like block diagrams, which is the easiest way to express it. So if you do it, be aware that they are doing something a little bit weirder than I would teach you guys. But it does not hurt to go look at it and kind of tinker with it if you need help, especially once we get into, there's a really fun assignment that you guys are going to have to build a multiplier coming up that is complicated, but very educational. It's one of my favorite assignments, actually. Okay, well, with that, since we have one strong opinion, let's go ahead and give you guys some lab time so we can migrate over that way, and I will putter around the lab and help you guys push on with the SPY project, because you all are now working on the SPY, right?
Yeah. Move on to it. I checked with 2 plot triggers on my.
Okay, yeah, it's very rare that you guys will design it with plug.
You're right. I thought that. Question myself once I said it. Yes,
Because it's possible, but it's hard in the state machine.
I,
Because you have to trigger it on the outgoing transition, not the entrance to the previous one.
yeah. I think I've done that before. That's where I was. But it didn't. Oh my gosh.